Hello all, welcome again. This is a session on Stm32H7 inter-integrated circuitry I2C or I2C as we commonly pronounce. I2C interface is compliant with the NXP I2C specification bus and user manual. So please subscribe to our channel by clicking subscribe button if you did not subscribe, and press bell icon for further notifications, personal notifications. Thank you. Let's move ahead. So the SMBus system management specification revision 2 and the PMBus system management protocol specification revision 1.1. This peripheral provides an easy to use interface with very simple software programming and full timing flexibility. Additionally, I2C peripheral is functional in low power stop modes as shown in this. So benefits are easy to use event management, fully programmable timing values, functional in low power stop modules. So you can see like we have I2C coming from SDRAM, DMA, and then to the various peripherals, namely sensors, various sensors or application processor. So the key features of I2C in STM32H7 is multi-master and slave capability, 20 milliamps output drive capability for fast modes plus. Controls all I2C bus specific sequence protocol, arbitration and timing values, 7 and 10 bit addressing modes, multiple 7 bit address support, optional clock stretching. Here you can see two pull up resistors to VDD, and we have two lines SDA for data and SEL for clock, serial data and serial clock, and master 1, master 2, multi masters and multi slaves. Okay, here's the start condition and stop condition with data 1 to data n and acknowledge or NACK. So I2C peripheral supports master, multi-master and slave mode. So I2C IO pins must be configured in open drain mode. The logic high level is driven by an external pull-up. So IO pin supports 20 milliamps, which we already discussed, and in slave mode configuration of the peripheral, the clock stretching can be disabled by software. The peripheral in master mode supports slave clock stretching and clock stretching from slave side as well. Okay, programmable setup and holds some other key features are programmable setup and hold times, programmable analog and digital noise filter on SEL and SDA lines, wake up from stop mode on address match, independent clock allowing communication baud rate independent from system clock. I2C for supports autonomous mode in D3. So here are the quick points. After you go through this, then we'll move on to the block diagram of I2C. So here is the block diagram of I2C peripheral available in the STM32H7. Now you can notice there are APB bus, 2 registers, and within the I2C there are P clock and SMBA and clock control, data control and clock control we have, and I2C clock comes from RCC or P clock or PLL underscore or underscore clock, HSI kernel and CSI kernel, and all put together you get it into the I2C clock. And clock control will have GPIO logic and then analog noise filter and digital noise filter, and then it comes into the clock control. So this is the block diagram. Okay, the registers are accessed through APB bus, and the register peripheral is clocked with I2C clock, which is independent from APB block. The I2C clock can be selected from among the PLL, APB clock, the high-speed internal RC oscillator with a frequency from 8 to 64 MHz and low power internal 4 MHz RC oscillator. Analog and digital noise filters are present on SCL and SDA lines. A 20 milliamp driving capability is enabled using the control bits in the system configuration registers. You can see on the right top. In addition, an SMBus alert pin is available in SMBus mode. So let's quickly talk about I2C programmable timings. Full flexibility in timing generation. Here you look at this diagram. Setup and hold times between SDA and SCL lines during transmission are programmable through PRESC, prescaler, SDA del and SCL del fields in I2C timing registers I2C underscore TIMING R. Timing R. This is considered to be a timing register. So SDA DEL is used to generate data hold time, that is T SDA del equals to SDA del star prescaler plus 1 and star TI2C clock. SCL del is SCL del plus 1 star prescaler plus 1 star TI2C clock. So you can see here SCL falling edge internal detection, and this is how the I2C setup. After the data is sent, the clock line is stretched low during the programmed data setup. The total data hold time is greater than the programmed SDA del counter. This is due to the fact that the SDA del delay is only added once the SCL falling edge is internally detected. The time T-sync1 needed for the internal detection depends on the SCL falling edge. The input delay due to the filters and the delay due to the internal SCL synchronization with I2C clock. However, the setup time is not impacted by these internal delays. Okay, we just saw programmable timings, and these are all the points to be noted, and then we'll quickly move on to the I2C master clock generation. So this is the master clock generation. The I2C master clock low and high level durations are configured by software in I2C timings register. Okay, the SCL low and high level counters start after the detection of the edge of the SCL line. This implementation allows the peripheral to support the master clock synchronization mechanism in a multi-master environment as well as the slave clock stretching feature. Therefore, the total SCL period is greater than the sum of the counters. This is linked to the added delays due to the internal detection of the SCL line edge. These delays T-sync1 and T-sync2 depend on the SCL falling or rising edge, the input delay due to the filters and the delay due to the internal SCL's internal synchronization with the I2C clock. I repeat, this is the total SCL period is greater than the sum of the counters. This is linked to the added delays due to the internal detection of SCL line edge. These delays T-Sync1 and T-Sync2 depend on the SCL falling or rising edge. The input delay due to the filters and the delay due to the internal SCL synchronization with the I2C clock. The rising edge depends on pull-up resistors and SCL line capacitance. The falling edge depends on I/O port parameters defined in datasheet. In order to properly configure clock speed, these edges can be either measured or calculated. They are needed in order to properly configure I2C peripheral or I2C peripheral in the STM32Cube MX tool. Then the settings of the timing registers can be automatically calculated to this tool. So whatever points discussed, here is it. Then we will move on to the slave address mode. So I2C can acknowledge several slave addresses, two address registers, that is I2C, OAR1. The slave addresses are programmed in two registers. One address register 1, OAR1, can be programmed with 7 or 10-bit register. One address register 2, that is OAR2, can be programmed with 7-bit address, but least significant bits of this address can be masked through the OA2 MSK register. Okay, OA2 MSK register in order to acknowledge the multiple slave addresses. The two own address registers, that is OARs, can be enabled simultaneously. Okay, so here is it. So we will talk about to wake up from stop mode on address matches after this. So when I2C clock is set to HSI or CSI, the I2C is able to wake up the MCU from stop mode when it receives its slave address. So all addressing modes are supported. So here you can see like only the analog noise filter is supported when the wake up from the stop feature is enabled. All addressing modes are supported here. When the device is in stop mode, the high speed internal oscillator is switched off. When a start condition is detected, the I2C peripheral enables the high speed internal oscillator, which is used to receive the address on the bus. After an address is received in stop mode, a wake up interrupt is generated if the address matches the programmed slave address. So if the address does not match the high speed internal oscillator, if the address does not match the high speed internal oscillator is switched off, no interrupt is generated and the device remains in the stop mode. Clock stretching must be enabled because the I2C peripheral stretches the clock line low after the start condition until the high speed internal oscillator is started. After having received an address that matches the programmed slave address, the I2C peripheral also stretches the clock line low until the STM32H7 device is awakened. Simple, isn't it? So here are the parts. Then we'll move on to the simple master mode management. So master mode software management is very simple. Only one write action is needed to handle a master transfer with a payload smaller than 255 bytes. The full protocol is managed by the hardware. In order to start a transfer in master mode, I2C control register 2 must be written with start condition request. The slave address the transfer direction, the number of bytes to be transferred, and the end of transfer mode. End of transfer mode is configured by AUTOEND bit, auto end bit. If it is set, the stop condition is automatically sent after the programmed number of bytes is transferred. So if auto end is not set, the end of transfer is managed by the software. After the programmed number of bytes is transferred, the transfer complete TC flag is set and an interrupt is generated if enabled. Then a repeated start or stop condition can be requested by software. The DMA transfer can be managed by interrupts or by the DMA itself. Excuse me. Have a look at it, and then we will go with an event management after this. Note down the points if you require. Let's quickly move on to the event manager. So when the payload is greater than 255 bytes, the reload bit must be set in I2C control register 2. In this case, CR2 means control register 2. I2C underscore CR2 means control register 2. In this case, the transfer complete reload, that is TCR flag, is set after the programmed number of bytes has been transferred. The additional number of bytes to be transferred is programmed when the TCR bit is set, and then the data transfer will resume. The I2C clock is stretched low as long as the TCR bit is set. The reload bit is used in master mode when payload is greater than 255 bytes and in slave mode when slave byte control is enabled. When the reload bit is set, the auto end bit, AUTOEND bit, has no effect. You should note this point. When the reload bit is set, the auto end bit has no effect. Here is a quick points which I just discussed. Then we will move on to the slave mode. So by default, I2C slave uses clock stretching. The clock stretching feature can be disabled by software. In receive mode, the slave acknowledgement on received byte behavior can be configured when slave byte. Control mode is selected together with the reload bit being set. When the SBC bit is set, the number of bytes counter is enabled in slave mode. Clock stretching must be enabled when slave byte control is enabled. In receive mode, when slave byte control is enabled with the reload bit set and the number of bytes to be transferred is 1, the transfer complete reload flag is set after each received byte and the SCL line is stretched. That is, clock line is stretched. This is done after data reception and before the acknowledgement pulse. The receive buffer not empty flag is also set so the data can be read. In TCR subroutine, an acknowledgement or not acknowledged, that is NACK or ACK, can be programmed to be sent after the byte is received. It is recommended to clear the SBC bit in transmission as there is no use for the byte counter in I2C slave transmission mode. Whereas in SMBus mode, a slave byte control mode is used in transmission for sending the packet error code byte, that is PEC byte. Okay. So let's look at seamless SMBus 2.0 support available in Stm32H7. One is address resolution protocol, ARP, device default address arbitration in slave mode, host notify protocol support, that is host address, alert support, that is alert pin and alert response support, timeout and bus idle detection happens in this alert support, command and data acknowledgement control in SBC mode, PAC, that is packet error checking, hardware calculation. Okay, let's dig a little deeper into the PEC, packet error checking. Automatic PEC sending or checking n bytes, that is data transfer counter, is used to automatically check the packet error in reception after n bytes minus 1 byte are received. If the received PEC byte does not match the calculation, a not acknowledged is automatically sent after the PEC byte. That is NACK is sent after PEC byte. In transmission, the internally calculated PEC byte is automatically sent after n bytes minus 1 byte. Slave byte control mode must be enabled in slave mode in order to enable the n bytes counter and allow automatic PEC reception or transmission. Okay. Then we will quickly jump onto the interrupts and DMA, and then with okay. So interrupts and DMA. Here look at interrupt event and description parallelly. The receiver, several events can trigger an interrupt, right? The receive buffer not empty is set when the receive buffer contains received data and is ready to be read. The transmit buffer interrupt status is set when the transmit buffer is empty and is ready to be written. The stop detection flag is set when a stop condition is detected on the bus. The transfer complete reload flag is set when the reload bit is set and n bytes of data have been transferred. The transfer complete flag is set when reload and auto end bits are cleared and n bytes of data have been transferred. The address match flag is set when the received slave address matches one of the enabled slave addresses. The NACK, that is not acknowledged, is received or set when a not acknowledged is received after a byte transmission. DMA requests can be generated when the receive buffer not empty or transmit buffer empty flag. Okay, we will see at error interrupts events also. So bus error detection is set when a misplaced start or stop condition is detected. The arbitration loss flag is set in the event of an arbitration loss. An overrun or underrun error flag is set in slave mode with clock stretching disabled when an overrun or an underrun error is detected. In SMBus mode, a PEC error flag is set when the received PEC does not match the calculated PEC register content. A timeout error flag is set when a timeout or extended clock timeout is detected. An error pin detection flag is set in SMBus host configuration when the alert is enabled and a falling edge is detected. Okay. So let's quickly move on to the low power mode. In I2C is active in run and sleep modes. You can see in this table. In stop mode, the peripheral clocks are off and the register content is kept. Okay. In standby mode, the peripheral is powered down and must be reinitialized after exiting standby mode. Regarding the debug information, I2C SMBus timeout counter is stopped when the core is halted. Let's see some examples with STM32H7 here. I2C master in sleep mode to communicate with the sensors. I2C slave to communicate with the application processor. Here is an example of sensor hub application that requires several I2C peripherals. One or several I2C masters are used to interface with external sensors, and I2C slave is used to communicate with the application's processor. Let's see some of the instances features like 7-bit address mode, 10-bit address mode, okay, standard mode, fast mode up to 400 kilobits per second, and fast mode plus with 20 milliamps output, IO drive, IOs up to 1 bit per second and megabit, sorry, okay, independent clock, okay. For more information, refer to future trainings available on the peripherals like SIS configuration, system configuration controller, reset clock controller, that is RCC, and power controller, and NVIC interrupts, and the external EXT1 interrupt, direct memory access, and basic direct memory access controller, as well as low power D3 power. So thank you for watching this. Please subscribe to our channel by clicking subscribe button and bell icon for your personal notifications. Stay tuned for more onto the STM32H7 features and training tutorials. Thank you.